only way it can vibrate if I have the two atoms. Can't vibrate this way, they would just move. Right? Can't vibrate this way, they would just move. It's the only vibration which is possible for X1. If it were to vibrate this way, it couldn't, because it would just rotate. The rotation is wrong. So this is the only vibration it can. There is no degeneracy in vibrations if I have a diatomic molecule. If I don't have a atomic molecule, like a more complicated molecule like ammonia, then there might be degeneracy between the different hydrogens. But for diatomic molecule, no degeneracy. And if I want to look at the energetic states, then the ground state is not at zero energy for vibrations. Because Heisenberg tells us we can't know precisely where the atoms are, there needs to be some both momentum and energy uncertainty and so on. So the ground state for vibration is half the vibrational spacing above zero. Here, for the purpose of statistical mechanics, I said it and now we forget it. It doesn't really make any difference. In statistical mechanics, we can just define this is our energy zero. Not down here, but up here is our energy zero, and then we can say they're just a space from zero. If you really think about reactions between molecules, you can't do that. Because how far the state down here is, how close it is to zero, depends on how wide this parabola is. And if you have different widths of this parabola, if the vibration has more movement of the atoms or less movement of the atoms, then you'll find that this state goes up and down. So if I have a reaction, that energy from the vibrational ground state can be released and can be part of the reaction enthalpy. But we're not talking about reactions. So we just say our energy is zero, and we really say that we have now our E vibration, that is H times the fundamental frequency of that vibration, nu, times a quantum number, V, and the 1/2 we just forget. So it's really like everybody clear why we forget the 1/2? We can call it ground that always stays zero unless we are looking at reactions. Okay. And degeneracy was always zero. It's not degenerate. Each state is unique. Now, if that is the case, then I can immediately write what is the canonical partition function for that, right? That's the sum over now V e to the power of minus h times mu times v over kt, correct? That is then something which I can probably simplify. First of all, I can define myself a characteristic temperature of the vibration. I always like to define myself a characteristic temperature, something which has a unit of temperatures and which is indicative in which temperature scale am I really looking at. And so this one here, that would be my characteristic temperature. And I call it theta, capital theta, and it is for vibration. So what I have over here is the sum over all the vibrational states V, e to the power of minus the characteristic temperature for the vibration over the real temperature, and then I have this V over here, and you all know if I have it multiply something in the exponent, I can also take the whole thing to that power, so I can take that out here, correct? And the V runs from 0 to infinity. That is something which you did in your homework 2 weeks ago, remember? That is just a geometric series over here. That's just a geometric series, right? X to the power of 0, x to the power of 1, plus x to the power of 2, plus x to the power of 3, plus x to the power of 4, and so on and so forth. And you know the result for that. That is 1 over 1 minus e to the power of minus theta lib over p. So again, here now, we don't need to worry for our canonical partition function about summing. We no need to worry about it. It's all there. We have this all in one formula without the sum. There's a difference to what we did in notation. In notation, we had sums, and then we made an approximation and said, oh, the spacing is so close to each other, our characteristic temperature for the rotation was on the order of 2 Kelvin, so we can put them close together and then convert to an integral. That was an approximation. That was not reality. If we remember that we know that the file which we made the last time, we could look at that integral, and it was good if we were at high temperatures, but it was really bad if we were at low temperatures. We had lots of difference between the result at different temperatures. We had an offset in the energy over here, and we have that came from the beginning here, not being a cost, if you look at the correct way. This is not the case for what we just did over here. That is not the case for vibrations. Summing up that sum here, that is mathematically exact. That is something good to be done over here. So we don't really have that problem. Okay, so what we then need to do is we need to find theta what, and we need to put that into our formula over here. I think the theta rod corresponds to 14 150 centimeter to the power of -1, and now I should know what the conversion factor is, and I didn't write it down over here, but only the result. So I need to first figure out what the conversion factor is for that, and I think the conversion factor is this one here divided by this one. That gives me the factor I use times what I want to use over here. So this one here now gives me my theta what. This gives me my nu, and then the k we have. So then we can look at it. What is the lip? Now for the lip, we found that that is 1 over 1 minus the exponential of what's behind the order function. Oh, here's the lip, and that is h times nu over k with h times nu, the energy that is really h times nu what I have over here. H
equals 1 divided by 1 minus the exponential of minus, and I forgot still something, I forgot to make this. Okay, so equals 1 divided by 1 minus x of minus this one here divided by k. These two together would be our characteristic temperature for the vibration, and then also divided by the temperature, which is here. And close the exponential, close the parenthesis below, and we get a value like this. And now we can move it over to the side.
Okay. There's always one over here, nothing changes. Now, if I look at the temperatures which we are looking up here, the temperatures which we are looking up here are on the order of 5, 6, and so on. So we are at really low temperatures. So if I'm looking at Z, then we'll see the Z here. I can select some data still, and I can add into this one that we have here Z vibration, and the x-axis is temperature, and the y-axis is those values which we just generated over here. Then you find that the Z here is, for the vibration, is constant. In the beginning, it's the same value as we had for the Z for the rotation, when we did it precisely, but then it doesn't really change in this temperature regime. Up to 12 Kelvin, nothing happens. Now that is not too astonishing, because vibrational energies, which we saw, have a characteristic temperature on the order of 1000 Kelvin. So 12 Kelvin, pretty much nothing vibrates. So there is not really that big difference. But if I were to say, okay, let's start the temperature at 1 Kelvin over here, then we can already see that we have something else. Then we see that we have over here that, and this one here still stays relatively small. It just comes out to some higher values when you go to somewhere like 200 or so degrees Kelvin. So we are slowly approximating room temperature. If we then put 2 in over here, so then we can come to some place, but we might see some variation of the Z. The Z stays still very close. So we are really in a totally different temperature regime over here. So in order to show that better, let me duplicate this graph and take the other 2 lines out of the duplicated graph, and then see going to maybe starting temperature 10 Kelvin over here. And then you can see that at some temperature, the vibration starts to play a role over here. But if I have the characteristic temperature of a particular vibration of 1500 Kelvin, then we need to wait up to about 1500 Kelvin. Now, how did I come to 1500 Kelvin? 1500 Kelvin was H times mu divided by K. That was the characteristic temperature. And the vibration frequency, that is what you measure. How many wave numbers you measure in your Raman spectrometer or UCR spectrometer. Okay, then
once we have this one here, we can go on and see what else you can figure out. We can then see what needs to be the internal energy U of that. If I want to know what is the internal energy U of the vibration, then that is kT squared d ln of z by dt, correct? Now, if I have this as a problem, I know now that the z for the vibration is kT squared d ln of 1 over 1 minus e to the power of minus theta over t by dt. That is the result which we have. Okay. That's actually not so bad. So that equals kT squared. Let's do the external first derivative of the logarithm is 1 over that. So 1 over, and then 1 over 1 minus e to the power of minus theta over t. Okay, then the first derivative of this one here is that we need to look at this 1 over 1 minus and so on. And the first derivative of that one is, of course, minus 1 and then 1 minus e to the power of minus theta over kt squared. That is the first derivative of this one, the external one. Now, the first derivative of the denominator is minus e to the power of minus theta over t over 1, there is nothing here. And then the first derivative of what we have inside over here is minus q over 1. And then the first derivative of 1 over t is minus 1 over t squared. Would you have done the first derivative the same way? I hope so. I hope it's right. So these cancelled, and these two cancel, and these two cancel, and we have our k times that. But this one here we had defined, if you can still remember it, as h times nu over k. So times k, so the whole thing is really h times nu. And now let's see what else can we simplify over here. This is 1 over that. So this one is really in the numerator, correct? If it's in the numerator and here we're dividing back out of it, the square out of that one, then this here cancels against this one. And we have a 1 over 1 minus e to the power minus theta over kt. And we multiply that still with our e to the power of minus theta over kt. And the q we already took care of, that's the h nu, and everything else we've taken care of already. Now, this formula over here, we have the same e function here and here. So it's actually more convenient to divide by that e function and to see that is h times nu times 1 over. And now this one here divided by that one
dividing by an exponential just changes the sign in exponential, so that is e to the power of theta with over kt, and then this one here goes again away, -1. Okay, so here we have our formula for the internal energy, and it is not a particularly bad one. It is maybe inconvenient mass to do so, but it is not a really bad formula for the internal energy of our system. Right. Now, I'm maybe not going to do that today in the Excel file. That will be your homework, and I think you can do that. Now, if you wanted to know what is the heat capacity of your system, how do you figure out what is the heat capacity associated with the vibration? We had the formula which we can still see here for the heat capacity, where we take this this average over here minus that average. Those averages are only easy to make if we add up over states. They are not easy to make right now because we are not having individual states. We are summing up over. But it's not really a problem either, because we derive this one here coming from here. What from the heat capacity CV is the first derivative of the internal energy by the temperature. So if I wanted to figure out what is the heat capacity of our system, CV, then that is really du by dt. And for u, we just derive the formula over here, correct? So we just need to take one more time the first derivative by the temperature of that. And this time I don't think it's even as nasty as it was there. I think it's quite easy. But whatever I did, that is for you to do. So, for your homework, you will make your graph for the from Siebert, you will make a graph for the entropy, you'll make your graph for the heat capacity, you'll make a graph for the internal energy. You will do one more thing here, and that is the way I have set up this graph over here. I run into trouble, right? You see me running into trouble because these values here now, they are very different. And if I go to the temperature regime over here, I find very different values over here for my integral and non-integral value. You can maybe write out why that is the case. I think that would be helpful. It's not. It has to do with what I'm doing over here. Just why that is the case. Then we want ultimately to have a graph of the heat capacities. A graph of the heat capacities which goes from, so that you can see the heat capacity associated with translation, the heat capacity associated with rotation, and the heat capacity associated with vibration, all in one graph. And you need to kind of figure out what's the best way of doing it. Yeah, that will be the homework. Any questions for that? Okay. So this time it goes a little bit beyond what I'm doing here. And let me see if I can put this thing down. Because what you're going to find here for the heat capacity is that for the rotation, you had the step in the heat capacity at about the characteristic temperature for the rotation. And for the vibration, you will also find a step of the heat capacity at about 1/10 or so, 2/10 or so of the characteristic temperature for the vibrations. Here the step, if the characteristic temperature is here, the step starts much earlier. So that's what you're going to find. These two steps. I want to see in your graph these two steps. How tall are these two steps? You find they are both about K if you look at one molecule, or R if you look at mole of those molecules tall. So they have the same height, those two steps, but they occur at different temperatures. And you need to fidget a little bit with Excel to get that right. So if you were to put them together, what I want you to show in the end is a graph which has kind of these two steps. Not exactly at these temperatures. Now, we can also think about, let's look at electronic temperature. That's another degree of freedom. But for the electronic temperature, it's not really easy to derive formulas for a number of reasons. You all know the Rydberg series. The steps aren't equidistant in that anymore. The steps in energy are more complicated. And if I'm not looking at individual atoms, but if I'm not looking actually at hydrogen atoms, but if I'm looking at something more complicated than a hydrogen atom, pretty much anything, then I will find that I have the various different energies of 2s over 2p, and 3p is different than 3s. It's only the same energy for the hydrogen, and so the Rydberg series only works for hydrogen. So there's another complication in there. And then there's a complication that this is now 13.6 electron volts in total binding energy. So it's electron volt steps here in energy. The vibrations was hundreds of milli-electron volt steps. These ones here are electron volt steps. If they're electron volt steps, they're way, way, way too hot for real chemistry to take place. Those would be the electronic excitation just thermally. You have inside the flame, you have inside the combustion chamber, inside your internal combustion engine of your car, and there you might have them being relevant. Depending on what kind of chemistry you want to do, that might be very relevant or very little relevant. If you want to go to SpaceX and do the combustion chemistry in the engines over there, that's exactly where you need to do that statistical mechanics. But most chemists don't. And so for you who don't, for you, statistical mechanics involving electronic states will be by and large irrelevant. And so I'm not going to write about that. There are cases when states end up being really close to each other, like maybe these two states, and they could be relevant, but there's no general rhyme and reason for that. So, and there's only 2 states, 3 states or so generally, so we'll just do it. Okay, that now brings us almost to the end of the statistical mechanics chapter, except that we left a few holes here, and I'd like to plug those holes before I go on. So, in order to plug those holes, let's see. What we see on the left-hand side here, we never really talked about what is going on if I have the translation states. We said, oh, we use gas theory, correct? We never figured out what is Z for the translation, for the kinetic energy. And the reason we never figured out what is Z, the canonical partition function, for the kinetic energy is that those states aren't really countable. You can't really count. Now there is the 1 kilometers per hour state, and then there is a 2 miles per hour, and then there is a 3 meters per second, and so on state. There is, it appears at least, an infinite number of different states available. Does it mean statistical mechanics doesn't apply? No, it does not mean that. It just means that we need a different way to get our Z, which isn't really so bad. Because for the internal energy, U, we know from gas theory, that is 3½ kT, correct? That is what we derive for the translation energy. And we also know that that is kT squared d ln z by dt. We know both of these things. One of those, because it's a canonical ensemble and it's valid for all canonical ensembles, and this one here, because gas theory told us that already. Now, if that is the case, I'm interested really in what is going on here. And if I want to figure out what's going on here, I can cancel the k, I can cancel one of the t's over here, and I'll have then that if I separate my variables, I have 3½ of 1 over t dt equals d ln z, correct? Okay. Now, how do I do this best? Now I can integrate this whole thing, and I'll find 3½ and here it is ln t equals ln z. 1 over t dt integrated gives me ln t. And then there is an integration constant of some sort of integration constant c over here, correct? Integration constant sometimes. Okay, so now I would like to say one more thing about those logarithms. Rather than having my 3½ in front of the logarithm, I can also move it inside. The 3½ being moved inside is then t to the power of 3½. Logarithm is 20. Okay, now let's put the e function on both sides, correct? That is e to the power of ln of t to the power of 3½ times e to the power of c equals e to the power of ln z. Now e to the power of ln of t of 3½ that is e to the power of 3½ is t to the power of 3½ times e to the power of c, which is whatever integration constant we have, equals ln z. Equals z. So we know z already. At least we know how z depends on the temperature. We don't know a factor in z. There is a factor in z, that is e to whatever integration constant we have. But we know this is an integration constant with regards to integrating by t. So it doesn't depend on t, it's a constant. So the dependence of how that one z depends on t is t to the power of 3½. Now we also derived this formula over here for the pressure. Now, if we come for the formula for the pressure, then we can do the same kind of behavior and look how does how does z depend on the volume? We know here that PV equals nRT for a gas. So we know the result over here. We know here this is nRT divided by V. And we could do here nRT over V, that's P, equals KTD ln Z over VV. And then we find, okay, this here cancels. This here oddly cancels as well, because for the gas we have N, N is the number of moles, correct? So, times the gas constant, that is N times this NA, and then R over NA, R over NA is K. So N times NA, how many total gas particles we have? Over here, we assume the gas particles was only one, so N times NA needs to be 1. So this one here becomes K as well, and then K cancels over there. And then we are getting 1 over V equals ln Z, V ln Z. And then we can integrate that, goes exactly the same way as over here, but now we don't have the 3/2. We just have the power of 1. And we, this here, ln Z was T D N. We can figure that out, that here we need to have the V in this formula as well. And we still have an integration constant. So the takeaway message from this one is, if we learned something in a non-statistical mechanics way about our system, if we somehow still figured out what the pressure or what the internal energy of a system is, based on information which doesn't come out of those sums, we can use these formulas to construct out of that information some information about the Z, which is then not a sum, but some other way of making the Z. And then we can use it. And then still all our formulas of statistical mechanics are fun. Okay. One last thing, which we haven't done yet. That is, we didn't look here. The first question is, why is the formula for A, the Helmholtz free energy, so much easier than all the others? Why, if I'm looking at statistical mechanics, at the Helmholtz free energy here, I don't have a first derivative, I get it straight. All the other ones, I need a first derivative. The answer to that is, the Helmholtz free energy is a system where we work at constant temperature and constant volume. That is like our canonical ensemble, where we control the temperature of the ensemble and where we control the volume available for our system. So the Helmholtz free energy is the natural way of describing a canonical ensemble, and as a consequence, we don't need to have our complicated first derivative here. So that was an easy one. Now, how do we get to this formula? That is relatively straightforward as well. U minus T times S is A, correct? And then U is over here. T times S, T times U over T is U, so it's U minus U. U cancels. And then we just have minus KT ln Z. The T comes from here. So we get that right away from that. So the relation is relatively straightforward as well. Okay. At this point, I believe I covered all the bases in statistics. On Friday then, we are going to look how we can get an inkling out of statistical mechanics to how we actually use it. Whatever is on Friday's session will not be unlimited, but everything up to now will. Are there any questions? Homework, as I said here in class, which is a little bit more defined than what it says in the